I'm Adam.
I'm Joseph.
And I'm Gunner.
And this is Lab 8, shear plate interferometers and optical testing, and we are group 1B.
So these are the interferograms we expect to get for the different shear plates when different aberrations are present. So for the non-wedge shear plate, if it's collimated, we expect to get the null fringe, so either it's all white or all black. And then if we have defocus, we expect to get vertical lines. If we have coma, we expect to get a cross shape, and for spherical aberration, we expect the middle to kind of bulge out. And if we have astigmatism, when we say look at the X shear, we'll have a collimated beam, but when we rotate it to Y shear, we'll get defocus. When we go to the wedge shear plate, if it's collimated, we expect to see horizontal parallel fringes. When we have defocus, those fringes will either tilt up or tilt down, depending if it's diverging or collimating. For coma, we expect to get circles, and for spherical aberration, we expect to get this S shape. And if we have astigmatism, again, like say in the X shear, we'll get the collimated fringes, but then when we shift to the Y shear, we'll get defocused fringes. So first we want to test the non-wedge shear plate. So what we have is our laser going through our beam expander, and then what we did is we tested the collimation first with this 1-inch wedge shear plate, and then we got it as close as we could. And then what happened though is that when we take it off and it goes through our non-wedge shear plate interferometer, when we look on our viewing screen, we saw that we didn't have the null fringe. It looked something like this. And so what we did is that then we adjusted our collimating lens until we got to the null fringe, like so. And then we knew that we were collimated. Since we first collimated it with the wedged, and then we saw that it wasn't collimated with the non-wedged, this tells us that the non-wedged shear plate is more sensitive to collimation.
Starting from the null fringe, as we add defocus, the null fringe moves to the left or right. And so you get more and more fringes, and the fringes become more vertical. As decentering is introduced, the number of fringes remain constant. It just cycles through the fringes. So if we add both decentering and defocus, you will see the defocus and the decentering will cycle through the fringes.
So then we flip the collimating lens around, so now we have maximum spherical as seen on the 1-inch wedge shear plate.
As we add decenter, it cycles through the fringes and translates the image. Depending on which direction we add the defocus, the interferogram changes in different ways. If we add it in one way, the center bulge increases and then rings appear inside the bulge. And if we add it the other way, the center bulge gets thinner. If I have both defocus and decentering, I get the defocus interferogram and the decentering cycles through the fringes.
So this is the second setup. We have the laser right here, and it goes through a spatial filter, the collimating lens. This is the wedge shear plate. The light travels through the shear plate into our test lens, and the back focal point of the test lens coincides with the vertex of the curved mirror. Reflects off the mirror, comes back, and it causes this interference pattern at the very top.
We then added decenter and defocus to the testing mirror and observed the fringe patterns. But we had a problem where there was just so much coma where it was really hard to see what decenter and defocus actually did because coma just dominated the pattern. As we add defocus, the fringes move to the left and to the right. As we add tilt, it simply cycles through the fringes. As we add decenter, it also cycles through the fringes.
We then replace the reference lens with the testing lens, which is a plano-convex.
As we add defocus, the fringes move to the left and to the right. As we add decenter, it also cycles through the fringes. And so if we add defocus after adding decenter, the fringes move to the left and to the right.